Picture this. You pull out your phone, tap the icon for a social media app like X, and instantly, literally in the blink of an eye, your home timeline is right there. It's seamlessly populated with the latest thoughts, photos, and updates from hundreds of people you follow. It feels like magic, right? You just scroll and you consume. But beneath that millisecond loading time lies one of the absolute most fascinating, massive engineering mysteries of the modern digital age. In this explainer, we're going to tear down the facade of that simple scrolling experience. We're going to architect a social network timeline from the ground up, using real-world case studies and core principles of data-intensive applications. We're going to see exactly how these systems manage to survive under the crushing weight of millions of users.
Okay, so let's dive right into the core question here. How does a timeline actually load in milliseconds? I want you to really try to imagine the sheer mind-boggling complexity required to make this happen. When you open that app, the system doesn't just go and fetch one static document. Oh no, it has to instantly look at your specific profile, figure out the hundreds or maybe thousands of distinct accounts that you follow, dive deep into the database to find the absolute most recent posts from every single one of them, merge all of those posts together, sort them chronologically, and deliver them perfectly to your screen. And by the way, it has to do this for millions of people simultaneously, without the entire system just crashing to the ground. To really grasp how we build an architecture capable of that, we first have to understand the sheer scale we're dealing with.
And this number right here? This is our first reality check, 5,800. On a totally average day, in a social network functioning at the scale of something like X, users are creating an average of 5,800 posts every single second. Just stop and think about that for a second. Every time the second hand ticks on your clock, nearly 6,000 brand new pieces of data are injected into the system. If you zoom out, that amounts to an absolutely staggering 500 million posts a day. 500 million. Building a backend that can just store that amount of data is hard enough for sure. But building one that can instantly route that data to the right people, well, that is a whole different ballgame.
But wait, it actually gets much, much worse. Because systems can't just be built for the average everyday traffic. They have to be built for the absolute extremes. During special events, think of a massive breaking global news story, a huge sporting event, or a massive pop culture moment. That load can aggressively spike to 150,000 posts per second. This is the ultimate stress test for an engineer. If your architecture is brittle, this is the exact moment it literally shatters, taking the entire application offline right when people want to use it the absolute most. So, how do engineers actually solve this? Well, let's see how this builds out by first looking at the most obvious yet totally flawed way to construct it.
Let's look at our first concept, the relational bottleneck.
Okay, look at the three tables we have here. We've got a users table, a posts table, and a follows table. Now, if you've ever taken a standard database class, you'd probably instinctively try to solve this timeline problem using this traditional relational approach. And honestly, it makes total logical sense. But logic at a small scale doesn't always translate to survival at a massive scale. See, in a traditional SQL setup, to get your timeline, the system has to execute a query that jumps between these three tables. First, it queries the follows table to find out exactly who you follow. Then, it takes that list and joins it with the posts table to grab all their recent posts. Finally, it joins all of that with the users table to pull in the profile pictures and names, sorts the whole thing by the timestamp, and maybe limits it to the top 1,000 posts. It's an elegant, beautifully normalized schema. Literally no data is duplicated. But there is a massive, fatal flaw hidden right inside this design. Let's crunch the math real quick to see exactly why this breaks down. Say we want new post to show up on your screen within 5 seconds of being published. In this relational model, an online user's app would need to poll the database every 5 seconds. If we have, say, 10 million users currently online, that means the backend is being hammered with 2 million timeline queries every single second. But remember that complex join operation we just talked about? For a user following an average of 200 people, the database has to go fetch and merge posts from 200 different accounts. So 2 million queries per second multiplied by 200 followed accounts, that results in an overwhelming 400 million individual lookups per second. Guys, no relational database on Earth is going to handle 400 million complex read lookups a second gracefully. The relational model entirely buckles under the weight of its own reads.
Which brings us to our next major concept, the fan-out solution.
So this is a critical pivot point in our engineering journey. We have to completely flip our thinking to bypass this impossible read bottleneck. To solve this read problem, engineers use a concept called materialization, specifically implemented through a process known as fan-out. Basically, instead of doing the heavy lifting when you open the app to read your timeline, we do the heavy lifting when someone writes a post. Think of it exactly like the postal system dropping a physical letter right into a recipient's mailbox. We pre-compute your home timeline. We maintain a highly specific data structure just for you, essentially a cache, that acts as your personal timeline. When you open the app, the system doesn't do any of those crazy joins. Zero. It just looks at your mailbox and hands you the pre-computed list. It is incredibly fast.
Let me show you what fan-out looks like in practice. The user on the left makes a single post. Instantly, a background process takes that post and fans it out, meaning it pushes a copy of that post directly into the pre-computed timeline caches of recipient 1, recipient 2, and recipient 3. We are literally delivering the data to the followers ahead of time. So by the time recipient 1 requests their home timeline, that post is already sitting there, just waiting for them. We've essentially traded an incredibly expensive read operation for a slightly more expensive write operation.
But did this trade-off actually save us? Let's check the new math. At an average of 5,800 posts per second and an average fan-out factor of 200 followers per post, this new approach requires the system to perform about 1 million timeline writes per second. Now look, 1 million writes per second is still a massive, massive number that requires serious infrastructure. But compare that to our previous bottleneck, it is fundamentally a much more manageable engineering problem than trying to execute 400 million complex database reads per second. We solved the core scaling issue, or at least we thought we did.
Which leads us to our next hurdle, the celebrity problem.
Because just when you think you have a perfect, elegant architectural solution, reality throws a massive wrench into the gears. The fan-out model works beautifully for the average user with around 200 followers. But what happens when a user like Barack Obama with over 100 million followers hits post? If we use our standard fan-out system, the architecture suddenly has to generate 100 million copies of that single post and drop them into 100 million different mailboxes at the exact same time. The write load just massively spikes. The queues back up, everyone's timelines get delayed, and the whole system basically grinds to a halt just because one person pressed a button. The hard truth is, you simply cannot fan out a celebrity. So how do the absolute biggest social platforms survive this? By building a hybrid solution. First, for the vast majority of ordinary, everyday users, we keep doing exactly what we were doing. We fan out their posts to their followers' mailboxes. But second, we give celebrities a completely different set of rules. We do not fan out their posts. Instead, we store their posts separately in a global database. Finally, step 3. When you, the user, open your app, the system grabs your pre-computed mailbox of normal posts, it quickly grabs any new posts from the specific celebrities you follow, and it merges them together right at read time. By perfectly balancing the fan-out and the relational read, we survive the scale.
Now, there is one more layer of absolute genius here, and it's called hydrating IDs. Think about a viral post for a second. The number of likes, reposts, and replies is changing thousands of times a second, right? If we stored the actual like count inside your pre-computed timeline cache, we'd have to constantly overwrite your cache just to update a single number. That's incredibly inefficient. Instead, the timeline cache is heavily denormalized. That means we intentionally break standard database rules to prioritize raw speed. We intentionally omit certain details. The cache only stores the post ID and the sender ID. That's literally it. Then, at the exact moment you open your timeline, the system uses those IDs to quickly fetch, or hydrate, the actual text, the current profile picture, and the real-time like counts. This ensures your timeline is blazing fast, but that fast-changing data? It's always perfectly accurate.
Let's bring it all together now in our final section, Mastering Architectural Trade-offs.
We have unpacked an incredible amount of back-end complexity in this explainer today. But if there's one massive takeaway, it's that in the reality of software engineering, there are literally no perfect solutions. There are only trade-offs. Think about it. If you rely entirely on relational joins in a highly normalized schema, your system is going to be absolutely crushed by too many reads. If you rely entirely on materialized views and fan-out, your system will be completely overwhelmed by heavy write loads from extreme outliers, like our celebrities. The only true path to massive scalability is the hybrid approach. It's about deeply, intimately understanding your specific data, knowing exactly where your bottlenecks are going to be, and purposefully balancing normalization and denormalization. You have to constantly shift the boundary between the write path and the read path based entirely on the unique behavior of your users.
So I want to leave you with this final, somewhat provocative question. Knowing all these trade-offs, how are you going to architect your next big application? When you sit down to build a system, are you going to blindly reach for the standard relational database, or are you going to think critically about where your data needs to be fanned out? Are you going to anticipate the celebrities in your own datasets, the outliers that might completely break your elegant models? The next time you open a social app and see your timeline instantly populate, I really hope you appreciate the incredibly beautiful, balanced, and complex architecture running silently right under the glass of your screen. Keep learning, keep building, and we'll catch you in the next explainer.